We are next going to look at how we can use explanatory variables to help us understand our mean response associated with the Poisson distribution. So one could set up a regression model that looks like this, where mu is equal to beta 0 plus beta 1 times x, where let's say we only have one explanatory variable x. The problem with setting up the model like this is that for a particular set of beta 0 and beta 1 values and for a particular x, we could actually have a value resulting from them that is negative. And of course, mu cannot be negative. We cannot have a negative count. So what we need to do is work with the transformation of our equation here so that we do not have to worry about having a negative mu value. The transformation simply is to use the log of mu is equal to beta 0 plus beta 1 times x. This can alternatively then be written as mu is equal to the exponential function evaluated at beta 0 plus beta 1 times x. This then is referred to as our Poisson regression model. Now, if one wanted to, one could write this model in terms of let's say an ith observation. So we have mu sub I is equal to the exponential function evaluated at beta 0 plus beta 1 times x sub I. Of course, if there are p explanatory variables, then you have this linear combination of the regression parameters with your x's, your explanatory variables. Overall, what we have here is a Poisson regression model, and Poisson regression models are part of the class, the general class of models known as generalized linear models, where y has a Poisson distribution. Our systematic component is this linear combination of the betas with the x's, and our link function is the log transformation. Now, to find estimates of our regression parameters, our betas, we can use maximum likelihood estimation again. Our likelihood function, as written here, is a function of our regression parameters, and it's just simply the product of n different Poisson distributions corresponding to our n, our sample size of n, where we have the exponential function evaluated at negative mu. So in other words, I could write this as exp negative mu sub I raised to the y sub I power all over y factorial. Now, you don't see the betas in there because mu sub I is the exponential function evaluated at this linear combination of the betas with the x's. Now, for most situations, to maximize our likelihood function, we're going to have to use iterative numerical procedures to do that. The GLM function in R allows us to do this automatically. We've seen the GLM function before. We basically use it the same way, except for now where we have a family argument, we replace that with Poisson, link equal log. We can find covariance matrices the same way as before. We can also apply Wald and likelihood ratio inference methods associated with our parameters of interest. Okay, so let's take a look at an example where we can estimate a model. This is an interesting example dealing with horseshoe crabs and their satellites. And what this is going to be looking at is essentially the mating practices of horseshoe crabs. In particular, we're interested in the number of males, which are called satellites, that surround a female. So the number of males that are interested in females. Here's some more information on this whole process, the mating processes of horseshoe crabs. We are actually going to take a look at a short video dealing with this that comes from the Nature TV show that is on PBS. So let me go ahead and get the video and play it.
Horseshoe crabs prefer spawning in the cover of night, but this is the height of their short season. It only lasts a few weeks. They come to shore when the tides are highest to lay their eggs deep in the sand. Swarmed by hopeful males.
Okay, so this is an example.
The female digs.
There we go. This is an example where we can actually see the number of satellites surrounding a female. The number of satellites is actually going to be our response variable. It's going to be modeled with a Poisson distribution. So in this particular case, if you see where my mouse is, here's the female, and we have 1, 2, 3, 4, 5, 6, 7, 8 different satellites. So 8 different males that are interested in this particular female.
Down to bury her clutch. The males are smaller than the females, but they have a special claw that hooks onto her shell. Since fertilization is external, even unattached males will father some of the eggs. When her clutch is finally laid, the female breaks through the sand.
Okay. So what we're going to do then is, again, our response variable is going to be the number of satellites. That's going to be our y. And we're going to focus on one particular explanatory variable, the width of the shell or the backside of that female. We're going to call that x. So our model is log of mu is equal to beta 0 plus beta 1 times x. Let's look at how we can analyze this data in R, or do the computations in R, I should say. So let me come over here to 10. So I'm going to read in my data. It's in a comma delimited file. And I'm going to estimate my model using the GLM function. So I use, say, formula equal. There's my response variable, satellite, tilde with my explanatory variable. My data is in crab. And here's the change from what we've seen before. Family equal Poisson, link equal log. I then summarize the results that I save in mod.fit using the summarize function. And here we go. Let me come back over here to Word so I can write on it. Okay. So this output looks very familiar, looks very similar to what we had, for example, with the logistic regression model. Here we have beta hat 0, beta hat 1. In the standard error column, we have the square root of the estimated variance of beta hat 1. We have a walled test statistic corresponding to doing a test of beta 1 is equal to 0 versus beta 1 does not beta 1 does not equal 0. And then here is my p-value for that corresponding test. So what we have here is small p-value indicating that there's sufficient evidence to tell us that indeed the width of the crab is has an effect on the number of satellites around the female crab. So based upon this information, then we can write out what our estimated logistic regression model is. So there's the negative 3.3 right there. We have the positive 0.16. We have that right there. Of course, we put a hat on top of mu to indicate now this is my estimated model. Then we can also write the model as log of mu hat is equal to beta hat 0 plus beta hat 1 times x. Okay, so now that we've estimated this model, let's talk about some questions about it. What happens to the estimated mean number of satellites as the width increases? So notice how I have a positive value there. So that means as the width increases, then the number of satellites increases as well, the mean number of satellites. Well, what type of female crabs do male crabs prefer then? Well, it seems that they prefer the wider, let's say, backside of females because of what we see here in this model. So we can now apply what we've learned in chapters 2 and 3 to this new model here to do inferences, to find predictions and stuff like this. And so in the next, I think I have 7 questions here. We're going to go through that process, and the purpose here is to help you see that, for a variety of different models that one can look at in R, you're doing a lot of the same kind of code, you're kind of doing a lot of the same kind of inference procedures, so that when one gets outside of this course or go to a different situation that's not in my book, one can apply essentially the same techniques that we learned in chapters 2, in chapters 3, and now in chapters 4 to analyze those situations as well. So, question 1, what does a walled test for beta 1 conclude? We've already done that. There is sufficient evidence that width is important. How can we perform a likelihood ratio test then for the width explanatory variable? Well, we've looked at 2 functions in the past to help us do that, the little ANOVA function and the capital ANOVA function. We could use either of them here exactly the same way. Let me go to my program to illustrate. So let's look at the capital ANOVA function. Of course, it's in the car package. So I say ANOVA mod.fit. I say test equal LR for likelihood ratio test. And here we go. My negative 2 log lambda statistic is 64.91. 1 degree of freedom because I'm testing 1 beta. Here's my p-value. Very, very small. So there is strong evidence that width is important. Let me come back over here. So how can we then estimate the expected number of satellites when the shell width is 23? Well, we go back to our model. We write our model out, and where we had x before, we replace it with 23. Do the math, and you get 1.6. That's my mu hat. That's my estimated mean number of satellites. Well, how could we do this in R? Well, we can simply program that equation in, or we know of easier ways to do this in R. So for example, we could use the predict function in much the same way that we've done before. Let's see that. So I can say predict object equal mod.fit. New data is the argument where you put in, well, what are your x's essentially? In this case, I'm going to form a data frame that has a width variable of 23. This variable here has to have exactly the same name, what's in the original data frame. And then I'm going to say type equal response because I want to estimate essentially the mean response. And so when I go ahead and do that, I get 1.6, just like what we did with those by hand calculations, you could say. Well, what about finding a walled confidence interval for mu? How would we do that? Well, one way would be to do mu hat plus or minus the value from the standard normal distribution times the square root of the estimated variance of mu hat. We saw a very similar equation before when we didn't have explanatory variables. This has problems because it does not prevent, let's say, having a negative lower bound, which of course you can't have when you're dealing with counts. So instead, what we can do is first of all find then the interval for log of mu. Take it times the square root of the, take it times the quantile from the standard normal times the square root of the estimated variance of log of mu hat. Now, again, this is a little bit different from what we've seen before because now we're talking about the Poisson regression model, but the same principles apply. And there's my interval then for mu. How can we do that calculation in R? Well, we apply some very similar techniques to what we did when we found a confidence interval for pi from our logistic regression model. Excuse me. I'm going to use the predict function again, object equal mod.fit. New data contains my width of 23. But now I'm going to use type equal link. What that's going to do is give me a confidence interval for the log of mu. Then s equal true gives me my corresponding standard error that I need for the interval for the log of mu. So let's go ahead and do that. I'm going to put the results into lin.pred.hat. And so here is the estimate of the log of mu. In other words, beta hat 0 plus beta hat 1 times 23. Here's the estimated variance, the square root of the estimated variance of log of mu hat. With that then, I can find now the interval for mu itself. So I apply the exponential function to the what would be the lower limit. Let me actually just do that. There's the lower limit for my confidence interval for log of mu. I apply the exponential function to that. So now here's my lower limit for the confidence interval for mu. So I put that in results called lower, or object called lower. I do a very similar thing for my upper limit, and then I nicely summarize everything in a data frame. Here's my 95% confidence interval, 1.33 to 1.92 when width is 23. Well, what about profile likelihood ratio intervals for mu? Well, remember what we need to do for the MC profile package. We can use that here. So I'm going to first find an interval, once again, for beta 0 plus beta 1 times 23. And you can think of this as 1 times beta 0 there. Now, the way then we form our K matrix is that we take these coefficients for the betas and put them into a matrix form. Then we can use the MC profile function with our resulting fit from our model. And we have a coefficients or contrast matrix called K, which I formed there. I put that in there, and what this does, it calculates a whole bunch of negative 2 log lambda values, which then the conf_int function then uses to find my confidence interval for the log of mu. For some reason the scan, that's a little bit off. There we go. So here's my confidence interval for the log of mu. So log of mu, the upper bound is 0.647, the lower bound is 0.284. I can apply my exponential function directly to that if I wanted to. And now here is my confidence interval for just mu itself, 1.33 to 1.91. So I would expect with a width of 23, which is actually small in this particular data set, on average, the female crab will have about 1.3 to 1.9 different satellites around her. How would you estimate the covariance matrix and print it out in R? Well, same ways as what we've done before. Use vcov. How would you include some type of transformation of explanatory variables, such as interaction terms or quadratic terms? Exactly the same as what we've done with logistic regression. Okay, so let's now look at some plots of our data and the corresponding model. And so what I'm going to do here is do a scatter plot on my data first. So to do that, I'm going to use the plot function. The x argument is going to be the width of the crab. The y argument is going to be the number of satellites. I'm going to put a nice x-axis label, y-axis label. My main title of my plot is Horseshoe Crab Data Set with Poisson Regression Model Fit. And if you haven't seen this before, this is actually what's called an escape character. If I do /n, what that basically means is take this stuff right after it down to the next line. Escape characters are used, for example, well, that particular character is actually used in Linux, for example. And that's where that comes from. Panel.first equal grid, so I'm going to put some nice grid lines on my plot. And now I'm going to get my plot. Let's go ahead and take a look at it. Here's a scatter plot of my data. And so what we see roughly, there is maybe an upward trend in terms of as width increases, the number of satellites increases. I can go ahead and put my model on this plot too, where I use the curve function for my EXPR or expression argument. I write in the proper syntax the estimated model. So notice what I do is I grab out of mod.fit coefficients, where the first element is beta hat 0, the second element is beta hat 1. I'm going to make it red. I'm going to add it to the current plot. My line type equals solid, so it's just going to be a solid line. And this is what we get. And there's my estimated model there. Now remember what the estimated model is doing. It's estimating the mean. So we do see some, obviously, variation in terms of the observed responses around it. But what this model is doing is actually capturing this upward trend that we can kind of see from just looking at the scatter plot alone. Well, in a similar situation as this, when you have normal linear regression models, you want to have confidence interval bands also on the plot. We could include those too. Here's how. The first thing I'm going to do is construct a nice function that automatically calculates my confidence interval bands for me. So I'm going to create the function called ci.mu. It's going to have 3 elements: my new data, which corresponds to my widths, my model fit object, and alpha for whatever confidence level I want. So the next set of lines are exactly what we've seen essentially before when I found a confidence interval for mu, where I first found a confidence interval for the log of mu, and then I transformed it to be a confidence interval for mu. Again, this was a walled interval. And so I'm going to have the lower limit, I'm going to have the upper limit. And so what this function is going to do is return in a list format the lower limit and the upper limit. Let me go ahead and run that. Let's try it out. Let's try it out at a distance, or I'm sorry, a width of 23 and I get exactly what we had before. Now note, I could also run this function. Oops. Let me copy and paste this. I could run this function as well, where let's say I just want the lower limit only, so I can immediately extract the lower limit from the results. Oops. Hold on, I had some extra stuff in here. There we go. This is useful because I would like to plot the lower confidence interval band first and then do the upper confidence interval band second. So, lower confidence interval band, I use the curve function, where again I say expression, or expr, equal the results from ci.mu. And notice instead of putting 23 in there for the width, I put x. Remember how curve function works? It just puts in basically 101 different values possible of x, evaluates the function, and that's what it uses to do the plot. And then notice at the very end here, I'm automatically extracting the lower limit. I'm going to put it in blue, add it to the current plot, and make them dot dash lines. So let's go ahead and do that. And there's the lower confidence interval band. I could do the same thing with the upper confidence interval band and then put a nice legend on the plot. And the final plot, let's actually look at it in Word. There we go. So, for example, at, let's say, 23, if I go up to the bottom line and come over, you get the same confidence interval limits that we've seen before for a width of 23. Okay. Now, you may be alarmed by the number of these plotting points, meaning the observations on the plot, far from the estimated model. Again, remember, though, that we are modeling the average number of satellites per each width. So, as a kind of an ad hoc way of examining, let's say, the goodness of how well this model fits the data, what we can do is, let's say, find groups based upon our observed widths, so consecutive groups. And then for each group, how about we find the sample mean for that group? We plot it and then compare it to the model. So let's do that. So first of all, I'm going to find the minimum and maximum number of minimum and maximum width for these female crabs. And then to kind of automatically find these groups, I'm going to use a function called cut. And what I'm going to do is work with the widths, and I'm going to find groupings from 20 all the way up to 34, where I'm going to have 20 to 23.25, 23.25 to 24.25, 24.25 to 25.25, and so on, and then keep on going all the way up to 34. And I'm going to immediately put then the results into my crab data frame and call the corresponding new variable groups. So let me go ahead and do that. We're going to look at the head and tail of crab, and this is what we get. So the first observation had 8 satellites. The width was 28.3 for the female, and this one fits into my group of 28.2 to 29.2. Then 0 satellites, a small width, fits into my group 20 to 23.2. Okay, here you can see the last few observations, and overall you see that everything has been put into a group. Now, using these groups, what I want to do is use the aggregate function to find the mean y value, find the mean x value. So I use aggregate x equals satellites. I want to find the mean number of satellites by the grouping. Data's in crab. Again, I want to do this for the mean. I'm going to put that in an object called y bar. I'm going to do a similar thing for x bar, but now I'm going to have width instead. And then also I want to count the number of observations that fall into each group. So my fun is equal to length. So when the first places that we did this idea of using aggregate was with the place kicking data before. I'm going to put this into a data frame so we can evaluate it. And here we go. So for example, for the first grouping, the average number of satellites was 1. The mean width was 22.69 about, and there were 14 crabs, female crabs, that fit into that grouping. And so you can see then throughout the largest category, we have 5.14, mean count of 30.4 for the width. I'm sorry, that wasn't a mean count, that was just the mean width of the crabs. There were 14 crabs that fit into this upper group. Now I like to be able to add this to my plots. So in other words, I would like to plot the mean width with the corresponding mean number of satellites. Maybe I should put mean.satellite there. Unfortunately, I did not. So what I can do to add it to my current plot is I use a function called points, where I take the width, I take the satellite, I'm going to use a plotting character of 17, I'm going to make them dark green, 17 is actually triangles, and then I'm going to make them twice the normal size. Then I'll add a legend to the plot as well. So let me go ahead over here to Word so we can see the final result, and here we go. So we can see from this, the green triangles are the sample means for each category. And we see how the red Poisson model kind of goes through the middle of it. And so this is kind of an ad hoc way to say, yeah, it looks like my model is doing what I want it to do in terms of trying to estimate the mean count per width. If we were having large deviations of the green triangles from the red line, I would be a little bit worried. Okay, so does the data fit well? Well, based upon this ad hoc method, it seems to be, doing what it's supposed to be doing. This is not a formal measure of fit, but it helps. When you only have one explanatory variable, it helps to do a plot like this to get a general idea of what's going on. But you might be asking yourself, well, what if we use different groupings though? Well, my program gives some details about how we can, let's say, more automate the process of finding these groupings, maybe using quantiles of the widths for the female crabs. And if one were to do that, this is what we get. And we can see these green triangles are not fitting as closely to the red lines as we saw before, but still, it's not really too bad. But again, what the red line is trying to do is essentially kind of go through the middle of those green triangles. A little bit of a side note, one could also do a very similar plot like this in for logistic regression as well. And there are also some, you could say, formal goodness of fit tests that one could do that basically are based upon the same idea as what we saw here. Okay, so this set of notes gives you an introduction to Poisson regression models.